The mean value theorem. In calculus, the mean value theorem is kind of like what it says. It's the average value, as it means. The mean value theorem, what we're going to talk about here, is a guarantee. I guarantee it. It's something you can kind of say, I guarantee something's going to happen if you give me certain stipulations. So let me show you what I'm kind of saying. What comes with the mean value theorem are these two stipulations. If you have a function that's continuous on the closed interval, and the function is differentiable, meaning there's a derivative on the open interval, you can guarantee that there is a point at some point that has a slope from derivative equal to the slope between these two edges, between the coordinates at A and B on the interval. If I find the slope of that, there is some point that has that slope. Let me give you a little picture. I have a coordinate there and a coordinate there. If I have a function that's going to go between those two dots, a graph, all right, that is continuous, meaning the edges exist and I don't pick up my pen, and differentiable, meaning there's jagged edge, because non-differentiable would be a jagged edge. Basically, if it's differentiable, continuous, I can guarantee that at some point I'm going to have a slope equivalent to this secant line. So there's my secant line. So at some point, to get from here to here with a graph, I'm going to have a slope equal to this green line. I could have more than one, but I can guarantee at least one. So if you just think of any line, no matter how I draw it, at some point if I draw a line from here to here, it could go up and down as many times as you want, but can you see at some point I have a slope parallel to the green line? It could have a whole bunch, but at least one I can guarantee. Now, that is the mean value theorem. You're guaranteeing a point equal to the secant line. And from there, you can actually find that point as well. But that guarantee is pretty important when you're justifying things. And sometimes you have to justify yourself. And so the mean value theorem has an importance. All right. So does the mean value theorem apply for this function on the interval 0 to 3? If so, what value does it apply? What value or values does it apply on the interval? Okay, so our two stipulations are right here. Let's first start with that. Is this function continuous? Now you hopefully know your functions and know this is a cubic. And cubics are continuous. Now if there's a fraction, you have to worry about the denominator equal to 0. If there was a square root, you have to worry about those. But this is a continuous function. Another way to know if a graph is continuous is just think, could I plug any value from 0 to 3 into this function and cause an error? I can't. So I know, bam, it is continuous. So let's just write continuous on the closed interval 0 to 3, check. Yes, it is. You can put a yes. Yes! So part of it, I'm done. My first piece. Good. My next piece. Well, is this function differentiable on the open? Meaning, another way of saying differentiable is, would the derivative be continuous? If I take the derivative of this, the derivative would be, just kind of for the sake of thinking about it, is 3x squared. Is that derivative continuous? Is there any error on this interval when you plug in values? That's continuous. That's perfectly fine. Now if that confuses you that the derivative is continuous, let's just think, is it differentiable means, is there a derivative at all points on this? Does it always have a slope? Another way of saying, we'll always have a slope from 0 to 3 of this function. And if you know about this graph, yes it will. It'll always have a slope. So my next thing is it differentiable? Is it differentiable on the open interval 0 to 3? Yes it is. So I first, in my mind, see if my first two statements are true. If they are, I can go on. If they're not, I stop. So the question says, does it apply? Why, yes it does. Okay, so if so, where? So let's go to 3 and 4. To find out where it applies, what we have to do is we have to find the slope. We basically have to find our endpoints. We're going to find the slope of those two endpoints. And then we're going to set the derivative equal to the slope. So here we go. let's first find the slope. To find the slope, we need f of b minus f of a. So we need f of b and f of a. So let's find the function at a, so at 0. So I need f of 0, and I also need f of b, which is 3. So let's find those two values. F of 0, the original function, so that'd be 0 cubed minus 3, and here we have 3 cubed minus 3. What do we have there? Well, we have this one would be negative 3, 0 minus 3, and this is 27, be careful, minus 3 is 27 minus 3, 24. Alright, so that's f of b and f of a. Find the slope of those 2 points. Hopefully you realize these are coordinates. This might help to visualize. I now have a coordinate here, 0, negative 3, and 3, 24. Can you imagine a coordinate here? And I'm trying to find slope between these 2 coordinates. So let's find the slope of that. Alright, ready? M equals what? Well, f of b is this one, so 24 minus f of a, so minus a negative 3 over b minus a, so 3 minus 0. What's that slope going to be? Well, that becomes 27, that becomes 3, so my slope is 9. So my secant line, this little green line, whatever it is a slope of 9. And okay, so I find the slope through the point. Now I have to set the derivative equal to that. Okay, what was my derivative again? My derivative is this. So I'm going to set my derivative, remember, my derivative is 3x squared, equal to 9, and find out when does my derivative have a slope of 9. Because I guaranteed it right here. This guarantees I will have something on that interval. I will have a point that has a slope of 9. That's what the whole mean value theorem was talking about. I guarantee there's a spot. Okay, let's find that spot. So let's divide by 3, divide by 3. I have x squared equals 3. And then how do you solve this? What squared is 3? Don't you square root both sides? And I get x equals plus or minus the square root of 3. So, plus or minus the square root of 3, both these values will have a slope of 9. So you might think that's my answer. It's not. Because they're both of these on this interval. Gotta go back to this interval. No, only one of them is. Which one? The square root of 3. So what is my answer? Where does it apply? It applies when x equals the square root of 3. That is my answer right there. Not the negative 3, because the negative 3 is not in the interval. It is a point where you have a slope of 9, but it's not in the interval. So mean value theorem, if you have these two stipulations, guarantees a point where you have a slope equal to the secant line between the 2 points. So you first got to find a point, you got to set the derivative equal to the slope, solve it, and then make sure it's in the interval. You could have had a whole bunch of points that would be equal to that slope on the interval, but there's at least one with the mean value theorem. It's like a guarantee. I guarantee things are going to be a certain way. And it's nice to have little guarantees. When you buy something, it's nice to have a guarantee that something's going to work out. All right. An application of mean value theorem. Assume you take a steak that is 150 degrees off a barbecue, and then 10 minutes later, it is 100 degrees. Why must there be at least some point during the 10 minutes that the temperature of the steak was decreasing at 5 degrees per minute? So at some time on that 10 minutes that it decreased at 5 degrees per minute. How can I guarantee there's at least one point is decreasing at that rate? Now it could decrease faster than that, slower than that, because maybe it cools faster right at the beginning and then slows down. But at some point it will have a 5 degree per minute decrease of temperature. Now, why is this mean value theorem? Well, are you okay that at time 0, that's your temperature? At time 10, that's your temperature. Are you okay with a function, meet cooling? Can you okay with that being a continuous function? Meaning it's always going to just keep cooling. It's not going to all of a sudden get hotter unless it's over 150 degrees outside. Hopefully not hot. Are you okay that it's also differentiable? It's not going to all of a sudden have a slope that all of a sudden changes real quick, and it would also be a differentiable function. You just kind of imply it on both these. That, okay, mean value theorem applies. And if mean value theorem applies, well, can I find the slope of these 2 points? -5. Okay, so the slope is -5. And I said it's continuous on the closed and it's differentiable on the open, according to what I said earlier. Just that's kind of how steak or meat would get cooler. Can't I draw a picture? And that would be my secant line, right? The -5 slope. So isn't at some point on this interval, can't I guarantee, due to mean value theorem, at least some point my slope is going to be -5. Now, it could be a whole lot of time. It could be the whole time. But at some point, I have a slope of -5. So can I guarantee at some point my steak temperature is decreasing by 5 degrees per minute? Negative, decreasing? Why, yes, I can. And that's an application of mean value theorem. It guarantees something that is going to happen. And you can actually find out where possibly, not in this situation, because I don't have an equation for this decreasing temperature meat. Just an example. Good luck with mean value theorem. It's very practical.